Hello everyone. In this video, we are going to explore what is meant by a real interval, and we will see how we use real intervals to express inequalities. So a real interval is a continuous set of real numbers. What is meant by continuous? If we consider the real number line, which is the line that represents all the real numbers, any portion of this real number line is a continuous set, which means that there is no gap between the numbers in this real number line. If you choose any two real numbers in this interval, no matter how close these real numbers are, we will always be able to find another real number in between. So this is what is meant that there is no gap between the numbers. So a real interval is a continuous set of real numbers. So an interval of a real number x is simply a way to show all the values that x can take by using rectangular brackets or parentheses. When we say rectangular brackets, we mean these, and when we say parentheses, we mean these. In general, we use real intervals to express inequalities, and we also use them to express the domain of definition of a function, as you will see in the future videos. These are examples of real intervals. So we might have rectangular brackets on both ends, or parentheses on both ends, or parentheses on one end, and rectangular brackets on the other end. And of course, each one of these has a different meaning. If we have rectangular brackets on both ends, we call the interval closed interval. On the other hand, if we have parentheses on both ends, we say that this is an open interval. Now, if we have parentheses on one end and rectangular brackets on the other end, as the other two examples, these are neither closed nor open intervals. We say that they are half open or half closed intervals. Let us now see which inequalities each one of these intervals represents. If we have x belongs to the closed interval 1, 5, this means that x is between 1 and 5 with 1 and 5 both included. So x can take any value between 1 and 5 as well as 1 and 5. So in a closed interval, the endpoints are also included among the values which x can take. Now, how do we represent this on a real number line? Whenever we have a rectangular bracket or an equal sign on one end, we represent that by a full circle. So this means that 1 and 5 are both included. Then we join these two full circles, and this is how we represent a closed interval. And this is the region of all the values which x can take. If we have an open interval, this means that x can take any value between -3 and 4 without -3 and 4. So -3 and 4, which are the endpoints, are excluded. Now, how do we represent that on a number line? Instead of a full circle, we use an empty circle in this case. Then we join the two empty circles, and this is again the region of all the values which x can take. What if we have a half open interval or half closed interval? You might have guessed what we have to do here. So x in this case is between 0 and square root of 2, and the square root of 2 included. And this is how the representation of this interval on the real number line looks like. Similarly, we do the same thing for the other interval with an empty circle on -1 and a full circle on -15/4. Now, if it happens that at least one of the endpoints is infinity, we always open the interval at infinity. Why? Because infinity is not a real number. This means x cannot take this value. So these are some examples. For the first example, if x belongs to -∞3 closed at 3, this means that x is between -∞ and 3 with 3 included, or simply, we can just write x is less or equal to 3. How does the representation on the real number line look like here? This is how it looks like. So everything up to 3, with 3 included, are possible values for x in this case. For the other example, we do the same thing, but of course we open the interval at 4. So we say that x is between 4 and plus infinity with 4 excluded. Again, we can simply say x is greater than 4. This is sufficient to say that x can take any value right after 4 up to positive infinity. And this is how the representation on the real number line looks like. In the final example, we have x belongs to negative infinity, positive infinity. This means that x can be any real number. So we can simply say that x belongs to R. How do we represent that on a number line? It is simply everything, the entire real number line. We move on to the union and intersection of intervals. First of all, the sign of the union is the U shape, and the sign of the intersection is the inverted U shape. Union means or, and intersection means and. So if x belongs to AB intersection CD, this simply means that x must be between A and B, and x has to be between C and D. So x must satisfy both conditions. However, if we have a union, this means either x is between A and B or x is between C and D. It has to satisfy at least one of both conditions. Now I use closed intervals here, but of course we can replace that by open interval, half open, the same thing works. Let us do some examples. In the first example, we have x belongs to 1, 5 closed, intersection 3, 10 closed. Let us see how this looks like on the real number line. So we first list all the numbers in both intervals, but of course we have to respect the order. So we have 1, 3, 5, and finally 10. Now for the first interval, we have x belongs to the closed interval 1, 5, which means I have to use a full circle at 1 and a full circle at 5, and we join both full circles. For the second interval, we do the same thing. We have a closed interval at 3, 10, so we add a full circle at 3, as well as a full circle at 10, and we join both full circles. Now, since we have an intersection, this means we only consider the region where both segments overlap, which is this. So as a result, we can say that x belongs to the closed interval 3, 5. In the case of the union, since the union means or, and as we said, it is sufficient that x belongs to at least one of the intervals, in this case we consider everything where there is a segment. This means that x in this case belongs to the closed interval 1, 10. Now let us see the third example. In number 3, we have x belongs to minus infinity 0 closed at 0, union 0, 10 closed at 0. For the first interval, we add a full circle at 0, and we draw an arrow down to negative infinity. So that is the first interval. Regarding the second interval, we start at 0 as well, closed, up to 10, but 10 is excluded, so we add an open circle. Now where do both segments overlap? They only overlap at 0. So in this case, the only possible value for x is just 0. In the union case, as we said, we consider everything where there is a segment, which means that x belongs to the interval negative infinity 10, open at 10. In exercise 5, that is the representation of the two intervals. Is there any overlap? The answer is no, which means there are no possible values for x in this case, because there is no common value. So we simply say that there is no solution in this case, or in other words, as I mentioned, no possible values for x. However, if this is a union, we consider everything where we have a segment, as we mentioned before. So x belongs to the interval negative infinity 10, again open at 10. So in general, in the case of an intersection, if we have two circles on top of each other where one is full and one is empty, we do not consider the value because it is not a common value. However, in the union case, if the same scenario happens, we do consider it because again, the union is more flexible and it is sufficient that x belongs to at least one of the intervals. Finally, if we have x not equal to 5, what does this mean? If we say that x is different from 5, this means that x can take any values either less than 5 or greater than 5. To write this as an interval, the interval representation of this is the following. For the first part, we have x belongs to the open interval negative infinity 5, or means a union And x greater than 5 means the open interval 5 plus infinity, and this is how the representation on the real number line looks like. So that's everything about real intervals. In the next video, we'll see how we use these intervals in order to express the solution of linear and quadratic inequalities.